in terms of equations, and we've discussed in general terms some of the forces. We now turn to Maxwell's equations that describe the electromagnetic force and the Lorentz force that goes with that. And this is certainly the most important and well understood force that we have. The electric and the magnetic fields turn out to be two manifestations of one type of object, which we call the electromagnetic field, and are certainly inseparable. The force that arises from the electromagnetic field can be written in the following way. F is equal to a charge times the electric field plus the charge times the velocity across the magnetic field. This we learn and are very familiar with from freshman and sophomore physics, and it gives us the vector force in a non-relativistic form on the left, which would be, of course, the mass times acceleration of the particle. So on the one hand, we have Newton's equations, which will say mass times acceleration, or better yet, time derivative of the momentum of a particle of mass m and charge q is going to be the charge on that particle times the electric field at the point where the particle is located plus qv cross b at the point where the particle is located. The electric and the magnetic fields are generated by each other and by charge and current densities in Maxwell's equations. What do we mean by that? Well, there are two ways the electric and the magnetic fields can arise. One of those is by charges and currents that flow around, electrical charges and the flow of those charges, which constitutes currents. Secondly, they can generate each other. If we have a changing electric field, that can generate a magnetic field, and conversely. These equations are all represented in Maxwell's equations, which were formulated in approximately 1865. They take their integral form as follows. We have the integral of the electric field over a closed surface, the integral of a magnetic field over a closed surface, the integral of an electric field around a closed curve, where this is an infinitesimal line segment, and the integral of a magnetic field around a closed curve, where this is a line segment. We notice that in each case this is a dot product, so if we could imagine something, a closed surface that's something like, say, a sphere, and we look at the electric field everywhere on that sphere and take the dot product with a small surface element, which is in magnitude it's equal to the amount of surface we have there, a little infinitesimal square, and the direction is perpendicular to the surface and directed outward from the closed surface. There's never any ambiguity here on a closed surface because this vector is directed away from the inside of the surface and toward the outside. This equation right here says that the total flux, and this equation right here is the flux of the vector field E, anytime we define it. Anytime we see this equation, this defines the flux of a field E in general, in fact in mathematics. And we take the flux of the electric field through the closed surface, and that's going to give us always the charge that's inside the surface divided by epsilon naught, a constant. And what does that basically mean? Well, if you just think about something like a sphere as our surface, and then the electric field spews out from this charge that's inside, and the total amount of flux through that surface is the total charge inside. If, for example, we had an equal positive and an equal negative charge inside, the total flux would be zero because the vector sum of the charges inside would be zero. Basically, this equation, which is called Gauss's law for electricity, tells us that flux is generated by positive charges. Positive charges are the source of the electric field. This equation, which is Gauss's law for magnetism, says that there are no charges for the magnetic field, called magnetic monopoles. There are electric monopoles, mono meaning one or singular poles. And so there's no singular north pole that you can find that lives all by itself without the presence of a south pole. We always have those in concert, a north pole and a south pole making a magnetic dipole. If we take the integral of the magnetic field, therefore, over any surface, we always get zero. That means that the magnetic field lines that come into any closed container or closed surface are exactly equal to the magnetic field lines that go out. Therefore, the magnetic field lines always close in back on themselves and form closed loops. The electric field doesn't do that. It spews out of a positive charge and dives into a negative charge, which is called a sink. So those are, a positive charge is a source for the electric field, the negative charge is called a sink. The other two of Ampere's laws give us the integral of the electric field dotted with a line element around a closed curve. So we can imagine any kind of curve that goes around like a circle, and we take the electric field and dot it with a little length along that length and integrate it around that closed curve, and what we must get is the negative of the time derivative of the magnetic field through any surface, and this is a surface that is bounded by this closed curve. So if this is let's take this square right here, this rectangular kind of shape, as our curve C. Then we could take any surface that was bounded by this, going from here to here to here to here, and that surface S, the integral of the magnetic field through that surface would have a time derivative that was equal to the electric field around that closed curve, which tells us that if the magnetic field through this surface, that's the flux through this open surface right here, is changing, either because the magnetic field changes or because the orientation between this surface and the magnetic field changes, for either reason, this will give us a time derivative, which will give rise to an electric field that integrated around this surface is non-vanishing, which will give us a voltage. So we can generate a voltage around this closed loop by changing the magnetic field that dives through this loop. In other words, the total flux. In exact analogy with that, we can look at the magnetic field integrated around a closed loop, and that will give us two terms. One that's symmetrical with this term that comes from the time derivative of the electric field through here. So if the electric field through a open surface like this is changing, that will give rise to a magnetic field that integrates around the closed line at the border. But there's another term here, and this says that a current, I sub inside, that if we have a current that goes through this closed loop, so imagine an electric current diving through this loop, multiplied by the constant mu naught, that will give us an integral that's non-vanishing of the magnetic field around that loop. This is called Faraday's law, whereas the previous law was called Ampere's law. The charge inside for these equations is called Q inside, and the total current inside that goes through the loop is called I inside. These are called the integral form of Maxwell's equations, and someone should be able to reproduce these without any trouble at all, just writing them down from memory. They are so very important. And we should know also that these are Gauss's law for electricity and magnetism, Ampere's law, and Faraday's law. One should also understand that this term right here is called the Maxwell displacement current. And you can see from the term right here, mu naught, that this is also a mu naught times something else, which is like or similar to a current, called the Maxwell displacement current. And this term gives an equivalent current that flows in the event that we have a changing electric field. This is often demonstrated in freshman and sophomore physics with a current that comes along and then becomes a capacitor, and then the current flows along, and we can integrate the magnetic field B around the line, around the current here and around here. But what happened if we integrated it in the middle? The answer is we would have a changing electric field that would exactly compensate and give us the same result. One can use these equations, and I'll do that in another lecture, to go off from there and give examples of symmetric surfaces and how we can find the equivalence, for example, between this and the Coulomb's law, and how we derive that, and how we look at the magnetic field due to an infinite straight wire or a loop of wire. All of those kinds of problems can be worked that are highly symmetric using Maxwell's equations in their integral form. We're now going to derive Maxwell's equations in their differential form. One will recall that there are two vector theorems. One is called Gauss's theorem, the other is called Green's theorem. Gauss's theorem states that the integral over a closed surface of any vector field dotted with an infinitesimal surface element of that field is equal to the integral over a volume, and that volume is defined by the closed surface. It's the volume inside, so to speak, this closed surface. So this might be a sphere. This would be the volume inside a sphere. And so we integrate over that volume of the divergence of the vector field A and integrate that over the entire volume. And in physics, we often omit the triple integrals and sometimes just say integral over the volume. This is actually a volume integral, which is a triple integral. And the integrand, the differentials here are dx, dy, and dz, or dr, d theta, and d phi, or whatever three variables one has for that particular problem with that symmetry. Green's theorem says that the integral around a closed curve of any vector field dotted with dl is going to be the integral over a surface, open surface, bounded by the closed curve of the curl of the vector field dotted with an infinitesimal surface element. These formulas are familiar to you from your courses in advanced calculus, and we will move on without discussing those further. We know also, we need these two definitions, that the charge inside a volume is the integral of the charge density integrated over that volume, where the volume V is the volume contained by a surface that's closed. Rho is the standard notation for charge density. The current that's inside is given by the integral over a surface of the current density dotted with d sigma. If one imagines a surface S and an infinitesimal surface element d sigma with the current density that flows through that, that gives us the total current that flows inside or in through that particular surface. With that behind us, we can now begin to rewrite the integral form of Maxwell's equations as follows. First of all, you'll recall from our last equations that we had the integral over a surface that was closed of E dot d sigma is equal to the charge inside over epsilon naught. So we have taken this equation right here and rewritten it as 1 over epsilon naught, and rather than the charge inside, we have used this equation right here for the charge inside. Now we've also used Gauss's theorem right up here to rewrite this integral over E dot d sigma as the integral over a volume of the divergence of the electric field. So we just use this Gauss's theorem up here to write this in this form. Now, behind the scenes, why did we do that? We wanted Gauss's theorem because if you look at the right-hand side, this gives us a volume integral over the inside. This now gives us a volume integral over the inside of this surface. And remember, that was the restriction of Gauss's theorem. So, in fact, we have two volume integrals that we're going to be able to combine in just a minute. But that's the reason for all four of these equations written in the way they are written. The next equation, the integral of b dot d sigma over a closed surface is equal to 0, now converts with Gauss's theorem into this form here where the integral over the volume of the divergence of b is equal to 0. Next, we use Green's theorem twice for the other two equations. You recall that we had the integral of E dot dl was equal to minus d by dt of the integral of b over d sigma. Now that stays the same. It's the left side of this equation that we convert using Green's theorem, so that rather than having a vector field dotted with dl, we now have the divergence of that field, del cross E, dotted with d sigma. Again, you can see that what we've ended up with is two surface integrals over d sigma that we'll be able to combine. Finally, we have the integral around a curve of b dot dl, again by Green's theorem, is del cross b rather than del cross e. And the right-hand side has two terms. The one at the end, should have been an e there. The one at the end is the same as it was before. The one before that had mu naught times the electric current that was inside. Well, the current that's inside this loop by this equation here becomes the integral over the surface of the current density. And so what we end up with are these four equations here, and you'll notice that these are surface integrals, these are surface integrals, these are volume integrals. This is a surface integral over here. So in fact, we're going to be able to combine those with the following equations in the following way. By moving the right-hand terms to the left-hand side, we get the following results. That we can put everything here under the volume integral of del dot E minus rho over epsilon naught over d cubed x. This is a volume integral of this quantity here, and its integral over the volume V is equal to 0. Well, is there anything special about this volume? And the answer is no. This volume is any volume in space. And it turns out that if you have a volume integral that is arbitrary over any place in space, and it always is equal to 0, this can only occur if the integrand itself is equal to 0. Consequently, we can derive from this immediately that del dot E minus rho over epsilon naught has to vanish. Therefore, we get the equation del dot E is equal to rho over epsilon naught, the first of Maxwell's equations in differential form. Likewise, we get this equation, which tells us that simply that del dot B is equal to 0. Now you will recall that this is equivalent to the two Gauss's theorems, and this tells us that there are no magnetic monopoles. This tells us that the positive charges are the sources for the electric field, and there are no such sources for the magnetic field. Going to our third equation, we see that we have del cross E plus 1, the time derivative of the magnetic field, integrated over a surface. Again, this surface is arbitrary. Since this is any surface in the entire universe, or it's all surfaces, this can happen only if the integral over all surfaces in the universe vanish. That means that the integrand vanishes, which gives us the equation del cross E is minus dB dt. Finally, from the equation at the bottom, we get the same kind of result, and this should have had an E in it. And likewise, we can take this surface integral, which always vanishes, and recast it into this form. The incredible thing here is we now have a differential form of the four of Maxwell's equations. The important thing to note is that if we have in any vector field, and by vector field, remember, that's a vector which differs, which it depends upon the position and possibly the time, so it's a function of x, y, z, and t. If we have a vector field and we know the divergence of that field and the curl of that field throughout all of space, that determines the field exactly. Likewise, from our previous equations, if we know the surface integral over all closed surfaces and the line integrals along all closed curves in the space in the entire universe, that determines a vector field. We can write that in the following way. If we know del dot A and del cross A everywhere in space, that'll determine A. If we know the integral over a surface of A dot d sigma and the integral around a curve of A dot dl over every closed surface and curve in space, that will determine the vector field A. Thus, the methods that we have in Maxwell's equations are exactly what we need to absolutely determine both the electric field and the magnetic field throughout space, whether we deal with these equations in their integral form or in their differential form. Remember that these fields are vector fields, they're time dependent, and when we write E, we really mean a function of x, y, z, and t. And when we write the charge density, it's a function of x, y, z, and t. It varies from place to place and from over time. Likewise, the current density varies with time. When we write a vector field as a function like this, we really mean that it has three components, Ex, Ey, and Ez, each of which is a function of four variables. So this is actually a set of three functions of four real variables, and this is another set of three functions of four real variables. There are times when it is easier to use the integral form of Maxwell's equations, and there are times or other kinds of problems for which it's better to use the differential form. The integral form in particular, as I'll show in some other attached lectures that are not part of the main thrust of this course, the integral form can be used to very quickly find the electric field or the magnetic field in highly symmetric circumstances, using Gaussian boxes or surfaces over which we can perform these integrals very quickly because of the surface symmetry or the line symmetry of the problem. By that same token, there are times when the differential form, as we have written it right here, is much more important. And we're going to see that in just a few minutes when we begin to look at the vacuum solutions of Maxwell's equations. That is, solutions to this problem which in fact have no current and no charges anywhere in space, but we have an empty space and we're looking to see what type of electric and magnetic fields can exist out in a vacuum without having any sources whatsoever. For that problem, we'll need the differential form of Maxwell's equations. Maxwell contributed so much to physics because he not only gathered together all of these results that were derived from Coulomb, Ampere, and other scientists over a 100-year period, he then, you'll recall, added this one term and showed that these equations were self-sufficient, self-consistent, when this term called the Maxwell displacement current was added.